All right. Hello, class. Sorry I'm getting started a little bit late, I think. Um, I apologize for being a little bit late. And I also apologize for the internet issues last yesterday. Um, I hope that you were able to view the SL 514 lesson. Hey, Sebastian and Elena. I'm just gonna write that in case someone comes in part way. Please view the SL 514 lesson before this one because that has the background information. Okay, so this is might not make as much sense. Okay. Um, Hello, Matthew. Hello, Theo. Hello, Jin K. And hello, Geography Genius. Um, okay. So, yesterday's lesson, which, hey, Ava, which I repeat is the SL 514 lesson, was about a method of determining how far away a star is, and it was called the Parallax Method. Okay? And the Parallax Method, basically what you're doing with the Parallax Method is you are using the fact that the Earth is rotating around the Earth to view stars from different perspectives. Okay, and so what happens with the Parallax Method is as the Earth. So my head is the Earth going in its orbit. Okay, my head is the Earth going in its orbit, and as the Earth goes in its orbit, this thumb is a star, and from the perspective of my head, the star appears to be moving. Even though it's not, the star appears to be moving relative to the background, which in my case is the computer screen. Okay? You can try it yourself. Put your thumb out and move your head around, and you'll see that your thumb moves against the background. I wish I could see you all doing that right now, because if we were all in the classroom, we could all look stupid together doing this, but we can't since it's. Maybe we should do that on Zoom or something. So the limitation of the parallax method is that if a star is far away, as the Earth rotates, the apparent change in location of the star becomes so small that it is impossible to measure. Okay? So how far we can see stars is limited in the parallax method. So we came up with a different method. Okay? And it involves a couple of important points. The first, so fact one, is that the temperature of a star can be determined by its color. Okay? You've probably noticed this before. Have you ever heard that a red flame is colder than a blue flame? Okay? So the temperature of a star can be determined by its color. Okay? And there's a formula for this. The temperature of a star is equal to a constant of nature, which is 2.9 times 10 to the minus 3 meters Kelvin. This is the temperature of the star in Kelvin, okay? Divided by lambda, where lambda is the wavelength of the light that the star is emitting. Okay? Blue light has a shorter wavelength, so we can see that as the wavelength goes down, so it's a bluer wavelength, that means that the temperature goes up. Okay? So this is an important law because it allows us to take the temperature of a star, no matter how far away it is. Because we can look at the star through a telescope. We're looking at the star through a telescope, and we look at what its color is, and then we use this formula to get the temperature. And it doesn't matter how far away the star is, because if a star is red up close, it's going to be red far away. If a star is blue up close, it's going to be blue far away. So no matter how far away the star is, we can tell its temperature using this method. Okay? Fact 2. The apparent brightness oh, hey Vicky. Reginald wants a geography question. I'm going to ask what is the oldest mountain range in the world? That's my question for you. Okay. The apparent brightness, which is denoted by B for brightness, goes down the farther away a star is. Okay. And there's a nice equation for this. Okay. So the apparent brightness, B, is equal to L over 4 pi d squared. So d is the distance away from the star. Okay, so we can see that as d goes up, d is in the denominator, the apparent brightness goes down. L is called the luminosity, and it is equal to the power output of the star. Okay? So you could think about luminosity as how bright a star really is, and the apparent brightness is how bright it appears. Okay? Which, how bright it appears has to do with two things. It has to do with how bright is the star and how close is the star. Okay? You could have an incredibly luminous star that appears dim because it is so far away. All right? You could have an incredibly dim star appear bright because it is so close. All right? So this formula is really useful. Okay? Now, luminosity is, of course, measured in watts. Apparent brightness is measured in watts per meter squared. And so a telescope, so with the telescope, we can figure out, so temperature and apparent brightness are measured by telescope. Okay? A telescope can tell us what color a star is, and it can tell us how bright does the star appear. All right? Now here's fact 3. Fact 3 is that there is a correlation between the temperature of a star and the luminosity of a star. Okay? And the correlation is called, or the graph expressing the correlation is called a Hertzsprung-Russell diagram. Just named after two scientists. So usually this is just abbreviated as an HR diagram. Okay? How do we discover this correlation? We discovered this correlation using the parallax method. So the parallax method allowed us to figure out how bright are stars, and what is the luminosity of the star, and what is their temperature. Okay. Notice how if we know the apparent brightness and we know the distance, we can solve for the luminosity. So what we did, what scientists did, is that they used the parallax method to figure out how far away all these stars are that we can determine the distance to with the parallax method. And then we used this formula to calculate their luminosity. And we also calculated their temperature. And we made a graph of luminosity versus temperature. Okay? See how this graph has so I want everyone to look at the graph that I have in the lower left-hand corner of the screen. That's an HR diagram. And each point on that graph represents a particular star. Okay? And so we can see that there's a definite diagonal line running from the top left corner to the lower right-hand corner. Okay? Notice on the vertical axis is luminosity, and on the horizontal axis is temperature. So this expresses a correlation between temperature and luminosity. Okay? The units of luminosity are strange. See how it says L circle, like this. And this is called a solar luminosity. It's the luminosity of the sun, which is 3.8 times 10 to the 26th watts. Okay? I want you to notice that the scale on the axes is not linear. It's a logarithmic scale. So going up one tick corresponds to a factor of 100 increase in luminosity. I also want you to notice that on the horizontal axis, the axis is backwards. Okay? So what if a star was on the lower left-hand corner of the Hertzsprung-Russell diagram? That would mean that it has a lower left-hand corner. So left side is high temperature, low is dim. So these are the hot, dim stars. These are like the Megan Foxes of the stars, if you will. Okay? I always like to make celebrity jokes with the HR diagram. Okay? So lower left-hand corner, it's the dim but hot stars. If we go to the upper left-hand corner, hi Zena, those are the stars that are extremely bright and extremely hot. So I'm trying to think of who's a celebrity who's hot and bright. Probably maybe Paul Rudd. I'm going to put Paul Rudd in there. If we go to the upper right-hand corner of the diagram, this is the cool stars, low temperature, so they're cool and they're bright. Okay? So this is maybe the I'm going to say maybe the Seth Rogens of the, or not Seth Rogen, what's the other guy? Because Seth Rogen isn't bright, I don't think. I'm trying to, I don't know. Insert your own celebrity. And then in the lower right-hand corner, we have the stars that are dim and cool. So this one I know is the James Franco of the stars, okay? Because I think James Franco is a moron. All right. So moving on. So let me tell you the procedure for determining the distance to a star. Okay? We look at the star in a telescope. I have no clue who Phil Swift is. Okay, we look at the star in a telescope. And looking at the star in a telescope is going to tell us the two things. It's going to tell us the color of the star, which is equivalent to the wavelength of light that it emits. Okay? And then it is going to tell us the apparent brightness as well. Okay? With lambda, we can calculate the temperature, which is 2.9 times 10 to the minus 3 over the wavelength. Okay? Once we know the temperature, we can use the Hertzsprung-Russell diagram to relate the temperature to the luminosity. So we know what the luminosity of the star is. Okay? So we know the apparent brightness and the luminosity, so we can use this equation right here to solve for the distance. Okay? So we can take the apparent brightness and the luminosity and we can plug it into B equals L over 4 pi d squared. And we can solve for, so we know L and we know B, so we can solve for the distance to the star. Okay? And this method works for stars that are way further away than the parallax method because really all we need to be able to do is see the star. It has to be close enough to see it. And if it's close enough to see it, then we can tell how far away it is using this method. The parallax method, the star has to be close enough not only to see it, but also close enough where as the Earth goes around the sun, the star actually appears to move a significant amount. Okay? So this is a more powerful method. It allows us to see stars that are further, or to measure stars that are further away. So let's do an example. Let's see. So a star emits light of wavelength let's say 5 times 10 to the minus 7 meters. Okay. And has apparent brightness let's say the apparent brightness is 1.8 times 10 to the minus 18 watts per meter squared. How far away is it in light years? How far away is this star? Okay. So I'm just going to go through this flow chart. Okay. So both of these bits of information are obtained from a telescope. Okay. So first thing I'm going to do is I'm going to take the star's temperature. So temperature equals 2.9 times 10 to the minus 3 over the wavelength, which is 5 times 10 to the minus 7. And I get 5,800 Kelvin. Can I make, yeah. Okay. So that's roughly 6,000 Kelvin. All right. So now what I'm going to do is I'm going to go over to my HR diagram. Okay. And I'll annotate it here so you guys can see that. So I'm going to draw a line here. Oops. Draw a line. Here's 6,000 Kelvin, so I'll draw a line up. And I'm going to use this main diagonal. Okay. We're going to talk about what this main diagonal, what the main sequence represents in another lecture. But so I can see that sort of the intersection of the main sequence correlation with the temperature, and I'm going to read off the luminosity that's based on that. So let me draw a horizontal line here. So it's slightly more than one solar luminosity. Now you have to remember that this is a logarithmic scale. So halfway, if one tick mark is times 100, then halfway is times 10. So this is somewhere between one solar luminosity and 10. So I'm going to approximate it. I'm going to approximate the luminosity. So this means that the luminosity is approximately, I'm going to say 3 solar luminosities. So what would 3 solar luminosities be? Well, one solar luminosity is 3.8 times 10 to the 26 watts. So that tells me that the luminosity of this star is 1.1 times 10 to the 27th watts. Okay, so that's L. Now I'm going to use this formula. B equals L over 4 pi d squared. And I'm going to solve for D. So I have the apparent brightness is 1.8 times 10 to the minus 18. The luminosity is 1.1 times 10 to the 27th over 4 pi d squared. So I can solve for D. And I get about 7.1 times 10 to the 21 meters. And if you watched yesterday's lesson, the SL 514 lesson, then you know that 1 light year is 10 to the 16th meters. Okay, so I divide that by 10 to the 16th, and I get 700,000 light years away. So that would put this star in another galaxy, because our galaxy is about, the diameter of the galaxy is around 30,000 light years. So this would be far enough away that it's not in our own galaxy. This would be, maybe a satellite galaxy of the Milky Way. Okay? So I hope you enjoyed that. I hope it was enlightening, talking about light, to know how we know the distance to stars, because I think that's really interesting. At least, we can just look at a point of light and know how far away it is. That's pretty awesome. I hope you have a great afternoon, and I will see you tomorrow with additional ways of determining how far away a